So in the last class, we have gone through the basic concepts related to concurrency. And today we are going to extend the same discussion so that we can cover a few more concepts. So we have seen earlier that any transaction that we are having must satisfy 4 important properties. And what are those properties? We stated every transaction must satisfy these 4 properties, acid properties. So atomicity, consistency, isolation, and durability. And the concurrency control mechanisms basically deal with this isolation, right? So how to implement isolation, that we are going to study next. So as we have seen in the last class, the system prepares the schedules, right? So in fact, we are having a special program known as a scheduler, and that scheduler generates the schedules. So whatever are the schedules, those are generated by the schedulers, those must be serializable. So we have gone through the concept of serializability in the last class, and we mentioned 2 notions under this concept, and those were the conflict serializability and view serializability. As I stated, we are not going to focus upon view serializability, but we had at length discussion about the conflict serializability in the last class. So whichever are the schedules, those are generated. Those must be conflict or view serializable. Those must be recoverable, and for the sake of database consistency, preferably they should be cascadeless. So we have seen the concept of serializability in the last class. So today we are going to focus upon these 2 concepts, what we mean by recoverable schedule and what we mean by cascadeless schedule. Also, we are going to discuss how to test whether a schedule is serializable or not. Okay. So, a policy in which only one transaction can execute at a time generates serial schedules, right? So if we are having a policy wherein the rule is only one transaction can be executed at a time, then such kind of a policy always generates serial schedules. But if my policy is generating the serial schedules, then we are having poor degree of concurrency. So the throughput of my system would be very poor, right? Because whenever one transaction is executing, there is a lock on entire database. So meaning no other transaction can access the database. And that is why there is poor degree of concurrency. Only one transaction executing at a time. So if we go for some modern concurrency control schemes, they employ the trade-off between the amount of concurrency these systems are allowing and the amount of overhead that they incur. So obviously, if we want to have the concurrency in our system, then obviously, even though more than one transactions are working concurrently, the isolation property need to be satisfied. So to implement this isolation, we need to come up with the concurrency control schemes. And concurrency control schemes has the trade-off between the amount of concurrency they allow and the amount of overhead that they incur. So obviously, if we want to have some policy wherein concurrent execution of transactions is allowed, obviously the system needs to undergo some overhead, right? So there should be a proper balance between the amount of concurrency and the amount of overhead in the system. So concurrency control systems are usually looking after this trade-off between these two parameters, right? So we are going to discuss few such concurrency control schemes in our subsequent sessions, right? So few of these schemes are allowing the conflict serializable schedules to be generated, while other concurrency control schemes can allow view serializable schedules, but they are not allowing conflict serializable schedules, and so on. So whenever we go for concurrency control schemes, we are going to focus more upon what kind of schedules are being generated by making use of that kind of a concurrency control scheme that we are going to discuss, right? So before that, we are now going to see how to test whether my schedule is serializable or not. So in the last class, we talked about the conflict serializability. Right? So what we mean by conflict serializability, if I am having a schedule S, which is concurrent. So by swapping the series of instructions, or by swapping the non-conflicting instructions, non-conflicting consecutive instructions, if it is possible to come up with a new schedule S dash, which is serial schedule, then we say that this original schedule S, which is concurrent, is conflict serializable. I'll repeat once again. Initially, I am having the schedule S, which is concurrent. Okay, and if it is possible for me to follow the rule of conflict serializability, and if it is possible that by swapping the non-conflicting consecutive instructions, if it is possible to come up with the equivalent schedule, say S dash, which is a serial schedule, then we say that this original concurrent schedule S is conflict serializable. And always we want that our scheduler should create such kind of conflict serializable schedules, right? So let us see now how to test whether our schedule is serializable or not, because usually the length of the schedules is too big, and not only two transactions are participating in the schedule, but many number of transactions are participating in a single schedule. So similar to whatever we did manually by swapping the instructions, we come across the serial schedule and we said that this is conflict serializable. This way of working to check whether the schedule is conflict serializable or not is not feasible in the real scenario. So we should have some mechanism to test for serializability, whether the given schedule is serializable or not. So let us consider that we are having some schedule with the set of transactions, say T1, T2 up to Tn. So all those transactions are participating in some schedule, right? Now, what we are going to do out of this? We are going to draw a precedence graph. So what is a precedence graph? It is a digraph, or it is a directed graph, where the vertices of the graph are denoting the transactions. So we are going to draw a precedence graph wherein we are having the vertices in the graph. Those are representing the transactions. Those are participating in the schedule, right? So this graph consists of a pair of the form V comma E, where V is the set of vertices and E is the set of edges. So as I mentioned, the set of vertices consist of all the transactions. Those are participating in our schedule. So how to draw out the edges, right? So we are talking about right now the conflict serializability. So the set of edges consists of the edges of the form from Ti to Tj, for which one of the three conditions hold. So if I am having two nodes in my precedence graph, one node representing one transaction, say Ti, another node is representing another transaction, say Tj, then whether there is an edge in between these two nodes, how to determine, how to draw the edges in the graph. So we are having few conditions to decide whether we should have an edge between Ti and Tj. So when we are going to draw the edge, if these two transactions are having the conflict with respect to a particular data item Q, then we are going to draw the edge. For example, if Ti executes write Q before Tj executes read Q, so there is a conflict. Ti is executing write Q and then Tj is executing read Q. So there is a conflict. So if I am having such kind of a conflict, then I'll be drawing an edge between these two nodes, Ti and Tj. What is the other condition for conflict? Ti executes read Q before Tj executes write Q, or Ti executes write Q before Tj executes write Q. So if both the instructions deal with the same data item and both are right, or one of the instructions is right, then obviously we are having the conflict. And if there is a conflict, then we are going to draw an edge between this Ti and Tj. Right? So this is how we are going to draw the precedence graph. So let us see one example for that. So see here in this example, we are having one schedule, and in this schedule, two transactions are participating, and these are T1 and T2. So I'm having here few instructions from T1, then few instructions from T2 and so on. So this is a concurrent schedule. Right? And I want to test whether this schedule is serializable. Whether this schedule is serializable. So what I'm going to do is I'm going to draw such kind of a precedence graph. So T1 and T2 are participating in the schedule. So I'm having two nodes or two vertices in the graph, T1 and T2. Right? Now, see here, I'm drawing an edge from T1 to T2 and I'm naming this edge with the data item A. See carefully. I am drawing an edge from T1 to T2 and I am naming this edge, or I am labeling this edge with data item A. So why I am having this edge from T1 to T2? See here, T1 executes read A before this T2 executes write A. Right? T1 executes read A before T2 executes this write A. So read and write is having a conflict. and they are dealing with the same data item A. So for this data item A, there is a conflict between T1 and T2, and that is why we are drawing this edge from T1 to T2. Similarly, if we look for this another data item B, then this T2 is executing read B before T1 executes this write B. So once again there is a conflict, right? And this is why we are having an edge from T2 to T1, and we are labeling this edge with B because this conflict has arisen. This conflict is because of this data item B. Okay, so this is how we are drawing a precedence graph. So see here one more example. So in this schedule, we are having 5 transactions. Those are executing concurrently, right? And the data elements, those they are using are Y, X, Z, W, V, U, and so on, right? So if I want to have a precedence graph over here for this particular schedule, then what I'll be having is, see here, I'm having T1 is reading Y, and then T2 is writing Y. So from T1 to T2, I'm having this arc or edge. Further, this data item Y is being accessed by this transaction T4, right? So T2 is executing write Y, and then T4 is executing read Y. So once again there is a conflict, and we should have an arc from T2 to T4, T2 to T4, once again for this item Y. Okay, now if we look at this read Z, so Z item is being accessed by T1 and T3. So read Z is there in T1 and write Z is there in T3. So there is a conflict. So from T1 to T3, we should have an arc. Similarly, the same data item Z that is being accessed by T4, and that is why from T3 to T4, we are having an arc. So this is a partial precedence graph, right? We are not having, or we have not considered all the data items, right? But this is one sample of precedence graph. So you must have understood how to draw the precedence graph now. Now, once the schedule is given and once we have drawn the precedence graph, how we are going to make use of this precedence graph to check or to test whether our schedule is serializable or not. So a schedule is conflict serializable if and only if its precedence graph is acyclic. So what we mean by that? A schedule is conflict serializable if and only if its precedence graph is acyclic. Meaning, if we draw a precedence graph, and if in that precedence graph, if we are having a cycle, then we say that that particular schedule is not conflict serializable. But if we do not have the cycle in the precedence graph of a schedule, then we say that the schedule is conflict serializable. So if we look at this particular example, and if we consider this precedence graph, so we are having a cycle here. Is that correct? We are having a cycle here. So as we are having a cycle, we may declare that this schedule is not conflict serializable. Right? This schedule is not conflict serializable. Why? Because in the corresponding precedence graph, we are having a cycle. right? So this is the test for conflict serializability. So a schedule is conflict serializable if and only if its precedence graph is acyclic. So if we are having the schedule ready with us, and if we would like to test for serializability and specifically conflict serializability, then what we need to do is we need to make use of some cycle detection algorithms, right? So these cycle detection algorithms can find out whether there is any cycle in the graph. So you might have gone through such kinds of algorithms in your course related with computer algorithms, right? But there are certain algorithms, those are able to find out whether there exists a cycle in the graph. Okay, so we may go with that kind of algorithm to find out the cycles in the graph. Further, if precedence graph is acyclic, meaning there is no cycle, then the serializability order can be obtained by topological sorting of the graph. So once again, there is algorithm for topological sorting of the graph. So first we detect the cycle. If there exists the cycle, that means the schedule is not serializable. But if there is no cycle present, then we need to go for one more algorithm that is meant for topological sorting of the graph. So this algorithm will be helpful to determine the order of serializability. What we mean by order of serializability? The order of serializability meaning if I am having several transactions T1, T2 and T3, let us assume, then I may have the serial schedule like T1, then T2, then T3, or I may have the serial schedule like T2 comes first, then T1, then T3. I may have another order T1, then T3, then T2 and so on, right? So this topological sorting algorithm, what it does is it finds the order of serializability. So the given schedule is equivalent to whether this serial schedule or this serial schedule or this serial schedule. So in every serial schedule, the order of transactions is different, right? See, for example, for this precedence graph, we may come up with the serializability order as T5, then T1, then T3, then T2, and then T4. Here, so T5 is not conflicting with anyone, right? And here there is no cycle at all. So we can determine the serializability order. So what would be the serializability order? T5, then T1. So T1 should execute first, then T3, right? Now, T1, then T3. Now, see here, we are having an arc from T2 to T4, right? So T2 must execute before T4. So then T2 and then T4. So then T2 and then T4. So this would be the order of serializability. So such kind of serializability order can be determined by this particular algorithm, topological sorting. Right? So I hope you must have understood now this concept. May I proceed? Yes. May I proceed?
Yes, ma'am.
Right.
Yes, ma'am.
So now let us go through another concept, and that is known as recoverability. So what is the effect of transaction failures on concurrently running transactions? So we are having the concurrent schedules now, wherein more than one transactions are running simultaneously. So if one of the transactions fail, then what will happen? So what is the effect of transaction failures on concurrently running transactions? So always we prefer to have the recoverable schedules. So what we mean by a recoverable schedule? Let us see the definition. If a transaction Tj reads data items previously written by transaction Ti, then the commit operation of Ti appears before the commit operation of Tj. I'll repeat. If we are having two transactions Ti and Tj, and if transaction Tj is reading the data items, those are previously written by transaction Ti, then the commit operation of transaction Ti should appear before the commit operation of transaction Tj. So let us see the example. Suppose we are having this schedule named as R1. So in this schedule, we are having two transactions. Those are participating, T8 and T9. Right? So look at the instructions in these two transactions and the order in which they are being executed. Okay. Now, we will say that this schedule R1 is not recoverable if T9 commits immediately after this read instruction. What we mean by that? See here, this is T8 and this is T9. So T8 is reading data item A and T8 is writing this data item A. So whatever data item that is written by T8, that same data item A is now read by another transaction T9. Okay. Now, if it happens that after reading this data item, this T9 executes commit here itself, then what will happen? This transaction has read the item and written the item. That item is read by T9. So T9 has done something and then T9 has committed. Right? So if T9 commits early and afterwards we find that due to some problem, this T8 is failed. T8 is failed. Then what will happen? If T8 is failed after T9 commits, T8 is failed, then this T8 is rolled back, meaning all the updates are being reversed. So whatever was written by whatever was written by T8, that is also reversed, right? But as T8 has not committed prior to T9, T9 could read that updated value A. But now T8 has failed and it has reversed. It has rolled back. So in this situation, I will say that this schedule R1 is not recoverable. And if I am having such kind of a schedule, then my database may not be in consistent state. So the recoverability condition says that if I am having this kind of a schedule and here if T9 is reading something which is written by T8, then T8 should commit first and then only T9 should commit. So what happens here is if T9 T8 commits here and then T9 commits, then there will not be any problem because this is successfully done and whatever is written here, that is read by T9 and this also successfully commits. So there is no issue, right? But if prior to committing this transaction T8, if T9 gets committed, then we will say that this schedule is not recoverable. Got the concept? Yes. See, in this situation, I'll give you one more situation. So if this is the schedule, this has not been committed, this has also not been committed, and if there is a failure here, and due to this failure, T8 needs to roll back. So if T8 is rollbacking or reverting back and this has also not been committed, then what will happen? As T8 gets rolled back, T9 also gets rolled back. And that is why there is no harm in the database, consistency of the database. So in this kind of situation, if both the transactions are not been committed yet, right, and if there is a failure of T8, then obviously T8 needs to roll back, but as T9 has not been committed, there will not be any problem. If prior to this failure, if T9 gets committed here, and if T9 has read the data item written by T8, then there would be a problem, right? So please once again refer to this comment. R1 is not recoverable if T9 commits immediately after this read operation. But if T8 commits first and then T9 commits, then there will not be any problem. Okay, so once again I am reading the definition of recoverable schedule. If a transaction Tj reads data items previously written by a transaction Ti, then the commit operation of Ti appears before the commit operation of Tj. And if this is the case, then we say that this is a recoverable schedule. So even though there are failures, it is not possible to destroy the data set or the database, right? So as I mentioned earlier, if T8 should abort, then T9 would have read an inconsistent database state in this case, in this situation. So if it is committed here and after that, if there is a failure, then T8 gets aborted, but whatever was written by T8, that is already been read by T9 and the T9 has committed. So T9 has read the inconsistent database state. This should not happen, right? So I hope you must have understood this concept. May I proceed? So our database system must ensure that the schedules are recoverable. The schedules must be recoverable. So one important point that we discussed earlier, the schedules must be serializable. Now the schedules must be recoverable. Okay. So let me proceed now with one more concept, and that is the cascading rollbacks. So sometimes it may happen that a single transaction failure leads to a series of transaction rollbacks. So what we mean by that? So let us assume that we are having this schedule wherein 3 transactions are participating, T10, T11 and T12. Right? So in this particular schedule, none of the transactions are committed yet. So this schedule, we may say that this schedule is recoverable schedule, right? But if in this particular scenario, if my T10 fails here, so if my T10 is failed, then what will happen? See here, whatever is written by T10, that is being read by T11. Whatever is written by T11, that is read by T12, right? And after executing all those instructions, there is a failure of this transaction T10, the first transaction, right? Then obviously, if there is a failure, the system needs to abort this transaction T10. So obviously, what will happen? Whatever was written by T10, that is read by T11. So this transaction also need to be aborted. Also, whatever was written by T11, that is read by T12. So this transaction T12 must also need to be rolled back. Right? So even though this schedule is recoverable, sometimes it may happen that the series of transactions need to be rolled back because of failure of one of the transactions. And if such kind of cascading rollback, so this situation is known as cascading rollback. So if there are such kinds of cascading rollbacks, then significant amount of work can be undone, right? So while generating the schedules, we need to think of this parameter also, whether there are cascading rollbacks possible, right? And to confirm this, we are having one important concept, and that is known as cascadeless schedules. So my system should generate the cascadeless schedules, meaning the schedules wherein the cascading rollbacks cannot occur. Because if there are cascading rollbacks, then as we have seen earlier, significant amount of work needs to be undone. So this should not happen, and that is why we prefer to have the cascadeless schedules. So for each pair of transactions, say Ti and Tj, such that Tj reads a data item that was previously written by Ti, the commit operation of Ti appears before the read operation of Tj. See here, the modification in recoverable schedule and cascadeless schedule. In recoverable schedule, what we mentioned, if Tj is reading the data item written by Ti, then Ti should commit first and then Tj. Here, if we want to have the cascadeless schedules, how we are going to modify this condition? If Tj is reading the data item previously written by Ti, then the commit operation of Ti must appear before the read operation of Tj. So here, if T11 is reading this A and T10 is writing this A, then commit operation of T10 should appear first here before T11 reads that element. If this is the case, then there will not be any chance of cascading rollback, right? And such schedules are known as cascadeless schedules. So important point to be noted is every cascadeless schedule is also recoverable, right? And it is desirable to restrict the schedules to those that are cascadeless. Meaning, now we would like to ensure that whatever schedules are being generated by database systems, those are serializable, those are recoverable, and also we need to make sure that those are having this property of cascadeless, right? So the schedules should be generated which are satisfying these three properties. Okay, so I hope you must have understood these concepts. Any doubts so far? Yes, any doubt?
No, ma'am.
Right. So in the next class, we are going to discuss about actually the concurrency control mechanisms, and before that we'll be focusing upon some locking mechanisms. Those are being used in database management systems, right? So we'll be discussing about log granularity in the next class, and then we'll focus upon few different kinds of logs those we may have, and then we'll talk about some log based protocols, right? So this is what we are going to discuss in the next class. So let's stop today. Thank you.